welcome to the channel. YouTube tells me about 95% of you are viewing this channel for the first time, so welcome. My name is Greg Friedman. I'm a PhD in bioengineering, and on this channel I like to take deep dives into science, but keeping things practical and reasonable so we can actually chat about deep scientific questions. And this whole channel is kind of like an Ask Me Anything, so please feel free to leave a comment down in the description. I read all of them, and some of them turn into videos just like this one. So today, this morning, I got a question from Anonymous Comments number 5722. Welcome to the channel, friend. And it's actually 4 questions, and it's the 4th one that's the most, not intriguing, but curious for me to answer and curious by your reaction to my answer. So let's dive into this. Question 1. From what I understand, plasma doesn't show up on phase diagrams because it lacks the distinct sharp change that the other states do. Do you think plasma should show up on phase diagrams? Yeah. You know, there is a debate on where plasma actually starts, and there are so-called dark discharges where it's kind of plasma, but conditions aren't exactly right to call it plasma. And, you know, it's a couple of chapters of the plasma physics book, this question. But to me, as an engineer, think of like a welding torch, right? Like you go to Lowe's or Home Depot or whatever your local hardware store is, you pick up a welding torch. Can you tell me when it's on and when it's not? Because I can, right? Like you ignite the weld and there it is. A lot of stuff I do in my lab, it's very easy to tell. Plasma is off or plasma is on. It's pretty obvious. So even though it's very debatable where exactly plasma starts and what happens right before it starts, but think of it like ice melting in the river. There's a bunch of ice, but there's a bunch of water, so where does ice end and water or liquid begins? You know, to me, it's definitely a very distinct 4th state of matter and should be taught in our school systems more than it is currently. And anyway, you know, plasmas are everywhere. They are engines for spacecraft. They treat all of the clothes that I'm wearing. I treat it in plasma for painting, and I have a video about that. Plasmas are everywhere, so shouldn't we be teaching our kids about that? Thought so. So let's move on to the 2nd question. Does plasma move in the same way gases and liquids do? If it doesn't, have you seen plasma move in ways that strike you as unusual? Well, not anymore. I mean, I've been doing this professionally almost 25 years. So for me, plasma makes sense. You know, plasma is, especially so-called non-equilibrium plasmas, which are typically plasmas you see on planet Earth. Equilibrium being like the sun, where everything is in thermal equilibrium, temperature of ions and electrons are about the same, so everything is super hot. That's equilibrium plasma. Everything else is called non-equilibrium. And non-equilibrium systems, just like the name kind of sort of suggests, they're very complex. So you have soup of ions and electrons. Ions are positively charged. Some of them are negatively charged. Electrons are negatively charged. So electrons repel each other. Electrons are really, really tiny. So they can move much faster than ions. The metaphor I like to use is tennis ball and a building, right? So that's kind of the size ratio between an ion, an atom, and an electron. So no matter how fast tennis ball is, it's not going to affect the building much. It'll bounce off, and if you throw the ball at the building fast enough, it'll just punch right through X-ray electrons. But it's not going to move the wall. So there is some interaction, but generally ions go with ions and electrons go with electrons. Now ions, let's say positively charged ones, they're electrostatically repelled from each other. So plasma wants to expand. As a matter of fact, space plasmas, they're constantly expanding. The sun tries to break away from itself, but the gravitational pull pulls it back in together. So there's like this violent struggle. Does it move like liquid? Not really. The plasmas that you make on Earth move more like exactly where you direct them to move. Like the welding torch. It goes from the powered electrode to the grounded plate, and that's exactly where plasma flows. Plasmas, mathematically, when you do plasma modeling, you do describe them as liquids. Matter of fact, the name plasma comes from blood plasma because blood flows. Blood is an ionic liquid and it flows through your body. So electric discharge is just like blood without platelets and white blood cells and all of that. And in blood, that's called blood plasma. So that's where the name plasma comes from. And I think I did a video on that a few years ago, so if you search the channel, it'll be there. Anyway, and I hope that answers your question. And if it doesn't, please leave a comment down below and I'll be happy to think about a better response. Anyway, next question. There seems to be a wide array of different elements and compounds that are turned into plasma in industry. Are there any that you've worked with that were noteworthy, or any that you'd like to work on in the future? Well, all right, many, tons. So think of like a mercury UV lamp. So a 254 nanometer UV lamp. It's a vacuum tube. There are two electrodes on each side, and you turn it on. There is plasma, glow, so-called glow discharge, between the two electrodes in vacuum. And it glows, but you add a little bit of mercury. You add like a mercury bead that evaporates and emits light at 254 nanometers. So what you see from a UV lamp is actually mercury. I mean, I've worked with, for a while, for my PhD thesis, I did a lot of work with different gas combinations to try to study the effects of positive and negative charges and oxygen and nitrogen and helium. Oxygen plasma is the coolest. You need ultra high purity oxygen to get any contamination from nitrogen, even minute, tiny, 0.0001%, and you'll get purple glow, which overtakes the beautiful, pristine white of oxygen plasma. Like that was I literally ran around the building, collected all the grad students I possibly could find, and I showed them the white plasma. And most people weren't too impressed because, you know, it's like a nerdy thing to do. In the industry, yeah, there are tons of applications. Like when you're making an iPhone, most of that is done in different kinds of plasmas, surface deposition of different compounds. There's lots of cool different things you can add into plasma. My personal interest is plasma with aerosols. So not an addition of like a molecular gas or precursor for deposition, but addition of huge droplets, like micrometer-sized droplets. And very cool thing happens. You know, a particle that is less than a few micron, like on a few micron range. It is so small that the viscosity of air overcomes gravitational pull of Earth. So if you take like a 1 micron droplet and just let it go without convection, without air moving, it will take an extremely long time, maybe months, for the droplet to fall down to the floor. So these tiny droplets virtually feel no gravity at all. And if you put them in plasma, they get charged, they repel each other, and they form so-called Coulomb crystals. That was demonstrated on the space station by a bunch of scientists. And if you Google Coulomb crystals, it's a really cool effect. And we can sort of kind of replicate that on Earth using these micro droplets and sprays. And that's kind of a cool thing that I work on and off throughout the years. And your last question, transient luminous events look pretty cool. Is there anything you find interesting about them? Very curious topic for discussion for us. Here is where the meaning of PhD comes in. I spent my entire career, basically most of my adult life, working with plasmas. Very specific plasmas though. Atmospheric, pressure, non-equilibrium discharges. I rarely work in vacuum. It's not like I have something against it. Well, I do. I don't like working in vacuum. It's batch process. Like you have to wait for the thing to pump down and then you can't touch it. You can't grab it. It's really hard to get into that space. So everything is much slower. Equipment tends to be much more expensive because you have expensive pumps. So no, I don't like vacuum. So I prefer working with this very narrow range of plasmas. Only the ones that work at atmospheric pressure and only the ones on Earth. And funny story, when I was in master's program, another master's student 2 desks away from me, one day, I'm typing away and he just like yells, "Wow, holy crap," like just jumps up and drags me to his computer and shows me this picture. And I'm like, the hell is this? I was just like, oh my God, this is latest. Like the Hubble telescope just took this photo hours ago. Yeah, well, that's cool. And he's like, well, that's plasma. Yeah, it's plasma, but it's space plasma. It's millions of miles away. It's in deep vacuum. It's some kind of phenomena happening between distant rocks. It is outside of my... Is it cool? Oh, absolutely. Let's look at the picture of transient luminous events. It's a lightning on top of a lightning storm, right? So typical lightning, when I say lightning, you usually think of electric discharge between clouds and Earth, right? Clouds are charged, Earth is at the ground state. So when the charge is high enough, lightning comes from clouds to Earth. But there can be potential difference between cloud and stuff on top of the clouds, because that gets constantly ionized by space radiation. So there can be plasmas, not from cloud to Earth, but plasmas or lightnings from upper atmosphere down to the cloud. And those are called transient luminous events, I guess. I have wandered into those talks at conferences throughout the years. I've seen probably a dozen talks about these, and I usually come to a talk like this when I have no other subject that I can find at a conference. I'll go to space plasmas, generally it's outside of my realm of interest. And those, while they're not so much interesting to me personally, they are very important, because when you're designing an airplane, you need to, anticipate lightnings. And we know airplanes get hit by lightnings, but you also need to anticipate these transient luminous events, which are more rare. I think, I'm not sure here, but I think they're more rare than regular lightning. What happens to the coating of the airplane? How do electronics respond? Do you need radiation protection coating on your electronics, etc., etc., etc.? So I'm not saying they're not important. Is there anything you find interesting about them? Not something that I would want to defocus my career from atmospheric discharges and focus on space plasmas. Maybe one day, not today. So anyway, thank you for a wonderful question. Please, if you have comments or questions, post them down below. I always read them. I try to answer most of them, and the ones I find interesting, like today's topic, I make videos about them. Peace, y'all. See you in the next one.